The tropical air is flowing into Texas and giving us some very spectacular cloudscapes this morning. Welcome back to Forecast Lab. Let's take a look at what's happening around the country this Tuesday afternoon. Well, the dominant weather feature is this weather system in Iowa. Cold front extending down to Texas, but take a look at the push of cold air coming into that region. Where's it coming from? What's the high pressure that's driving it? Well, if we look back further west, not much of anything. Maybe a 10-15 millibar high around Dodge City there, but that's really not much at all. And in fact, the lee side trough is developing once again in Colorado. Now, there is more cold air if you get further west into the Great Basin area, but not much of that has moved eastward just yet. East of this weather system, we've got tropical air flowing up from the Gulf, 70s dew points coming into Mississippi and Louisiana there, and 60s all the way up into the Midwest. And if we take a look up in Canada, that tropical air is pretty far north. Here it is November, the middle of November, and they're getting 70s up there north of Montreal. I would say that's probably a bit unusual. Up to the north, yeah, there is some cold air up there. And in fact, if you go out to the west around the Canadian prairies, we've got a new Alberta Clipper moving southeast. And very likely that's going to be heading in one of these directions that we see right here. Here we have the 250 millibar constant pressure chart. This is a look at the top of the troposphere. And for those of you, our supporters who saw yesterday's webcast, we went over a lot of this content and we explained that this is a map showing basically the height that you would have to go to for the barometer to fall to 250 millibars. And that's going to be approximately 7 inches of mercury if you had a barometer that read that low. Now the heights are on the low side up in northern Canada, and that's due to all the cold air below. And remember, we talked about thermal advection. When you have cold air advection, that tends to lower the heights. Well, here we have basically just cold air, so the heights are low. And we have the opposite effect down south, warm conditions, and we get high heights as a result. And we can also think of these systems as low pressure aloft. There's a low pressure area aloft. We refer to it as low heights aloft, but it's basically the same thing, and it's even lower up north. So what do we have on the chart? Well, we've got a strong jet stream coming onto the Pacific coast there, rounding the curve in New Mexico, and then flowing north into the Great Lakes area and Quebec. I would say the jet axis is actually maybe from Amarillo up to Minneapolis. So if you're flying from Minneapolis to Dallas, it's probably going to be kind of a long flight due to the headwinds. Now there's also a long wave trough in the western U.S. The axis is roughly there, long wave ridge, the axis roughly there, and there's probably a long wave ridge further out in the Pacific, kind of like that. And embedded in that, we've got these small scale shortwave systems. There's a shortwave ridge, shortwave trough, flattening out that ridge. Looks like there's probably a shortwave ridge here, and looks like another shortwave trough there, another ridge, and so on. So the blue here, these are the long waves, and the red is the short waves. So now we're zeroing in on our subject, which is going to be fronts today. Well, to segue into this, jet stream from West Texas all the way up to the Great Lakes, that's going to be supporting a frontal system. Now, in the past, those of you who have been with this program, you've probably remember how we've talked about troughs and downstream ridges indicating where there's likely a surface system. And that's usually going to be upstream from the ridge, downstream from the trough, and along the jet axis, so roughly in here. Now, that's not always a hard and fast rule. Usually there's a little variation, but this would tell us probably the fronts are going to be somewhat like that. So that would indicate Topeka, warm front out to Illinois, cold front down to Texas. Now, is that the case? Kind of. The system's a little further east. The warm front does not really extend eastward. It extends all the way up to Quebec like that. So if we actually draw that stuff out, we get something a little bit like that. So it's roughly following the jet. And you can see the jet axis, which I'll put in green, is in the proper place along and to the poleward side of those fronts. But that rule of thumb does get us about where we want to be. Okay, first of all, let's take a look at our building blocks of fronts, air masses. We talk about that just about every day here on Forecast Lab. Here's a tropical air mass. And then west of the front, a polar air mass. These air masses are basically a large volume of air with similar temperature properties. Really what we're looking for is density, the same density. However, temperature tends to dominate that, and to a lesser effect, moisture. A dry atmosphere is denser than an atmosphere with water vapor in it. Now, that may seem unusual because we think of water as heavy, but if you look at the periodic table, water is hydrogen and oxygen. If you substitute that out with the elements that make up dry air, primarily nitrogen and oxygen, you're basically dealing with heavier forms of matter because as you move to the right and downward on the periodic table, your atomic mass increases. As compared to hydrogen, which is a very light element. So it makes sense that dry air is going to be more dense. But temperature is what's most important. I would say it's probably about 6 times as important as moisture. Our next concept is going to be transition zones. Well, the main air masses, we've already identified the tropical air mass out in the eastern U.S. That's going to be located right about there. The cold air, the polar air mass, is located in the northern plains. Now, in between, we have a transition zone where the air is changing over from one to the other. And that's going to be roughly in this zone right here. Again, we refer to that as a transition zone. It's neither one or the other. It's not tropical, it's not polar, it's in between. However, the properties are changing. We can also see that on the thickness chart, which we talked about in yesterday's webcast. That's where we have packing of the thickness lines, right in here. That's a transition zone. The air mass itself has very few thickness lines running through it. There's the tropical one. And on the other side, you can see the polar air mass has very few lines running through it. So that transition zone is closely tied to the surface front. In fact, it's located on the poleward side of the front. So the front is down here. The transition zone found poleward, or on the cold side. Our next topic is the frontal surface. And that's an imaginary area where the cold air, the transition zone, meets the warm air mass. Now, the surface intersects the ground along the surface front. That's pretty much common sense right there. So that's where the frontal surface intersects the ground, right there. To look at that aloft, we need to look at skew-ts, or cross-sections. What we're going to do is take a look at a cross-section from southern South Dakota down towards New Orleans. You can see that we're going to cross over and hit that frontal surface at the ground around Fort Smith. And if you know a little bit about fronts, you know that we're going to find the frontal surface aloft over the cold air. So here's Tropical Tidbits. They've got a neat little interface for building those cross sections, and I'm going to draw that out. You can see we're intersecting the front right there. Now let's look at the graphics. So here's our cross section running from South Dakota to New Orleans. Now already you can kind of see some action going on right there. Yeah, that's going to be the front. Now let's take a look at our quantities. We have the freezing line and also a couple of isotherms, I think the 12 and 16 below Celsius isotherms. And you can see how they kind of sit over the warm air mass at about 12,000 feet, and then they dip down into the cold air where it's colder. Isotherm aloft, up at 18,000 feet, dips colder over the cold air. So hopefully that makes sense. However, isotherms, those aren't very useful aloft because obviously if you move the air mass vertically, you're going to get different values due to adiabatic warming and cooling, and that'll start messing you up. What we have to do is use potential temperature, and that's basically temperature normalized to 1,000 millibars. It's moved dry adiabatically, and we can kind of compare it at different levels. And that's what we're seeing here. Now these are actually theta E. This is not true potential temperature, it's equivalent potential temperature. That's a measure of total heat in the atmosphere, including moisture and its potential for latent heat release. Now more properly, that's a measure of buoyancy. It's not really equivalent to density, so that's not what we're going to be looking at for fronts, but it's still useful. If we see a sharp gradient, we're going to look a little more closely, and in many cases that can actually be the front. So this obviously is a transition zone, and we can pretty much bet that the front is going to be running about like that. That is the frontal surface. Let's look at it on a skew-t. We're going to go to 39 north, 97 west. And you can see that what will happen above that station is we're going to be in the cold air. As we go aloft, we're going to get into the transition zone above 600 millibars. That's about 14,000 feet. And then we're going to hit the front itself at about 450 millibars. That's about 22,000 feet. And then we'll be up in the warm air. So let's check out that skew-t. So 39 north, 97 west. That's going to be right about there around, roughly around Salina, Kansas. And if we look at that skew-t, we can see we're in the cold air near the surface. We go aloft and we get into the transition zone, and we hit the top of the front at about, it's actually about 18,000 feet. And then above that, we're in the tropical air. And we know that's tropical because if we bring that down, sort of dry adiabatically, maybe a little bit to the left, that's my personal rule of thumb, that puts us at a surface temperature of about 28 Celsius, which is about 80 Fahrenheit. So yeah, that's definitely tropical air there. And so, yeah, the frontal surface is about right there. And we see a very low tropopause at about 300 millibars. Let's go back to that cross section. There I've identified the front. Again, we're using theta E. It's not the ideal contour to use, but we're going to do it. So the front is right there. That right there is the surface front. We can also have upper level fronts. 500 millibar front located right there, pretty much over Salina, Kansas. So if we went back to the charts, we would likely find an upper level front back in this area here. That's the 500 millibar front. The 850 millibar front would be in between. So 500 millibar front right there, the 850 millibar front here, the 700 millibar front. And you can see that that frontal surface slopes back up and over the cold air. Now we're often interested in what the slope of that frontal surface is. A lot of times that's referred to by forecasters. If we have a front that's like that, it's going to have very shallow characteristics and a very shallow slope. In other words, as we rise, the actual run is going to be very long. We can also have very steep fronts like that, associated with very deep air masses. In this case, with a certain amount of rise, we have very little run. You probably have read about rise versus run, maybe in mathematics or carpentry, stair making, stuff like that. Anyway, that's a property we use, rise versus run, which gives us the slope of the front. Here's a good example of frontal slope. In this example, the front, 300 miles back from the surface front, is about 3 miles above the ground. So 300-mile run for each 3-mile rise, that's 300 to 3, which is a 1 to 100 slope. Now, a very common slope for a front is 1 to 100. Sometimes we see 1 to 200, and that tends to be very common for warm fronts. And finally, there's the concept known as a frontal trough. A good example of a frontal trough is right here on the GFS model. You can see the isobars kind of kink southward, indicating a trough in that area. All fronts contain a trough, but not all troughs contain a front. That's pretty important to keep in mind. So if you're looking for a front, you're definitely going to want to put it in that trough. But if you have a trough there by itself and you're not really looking for a front, you don't want to actually turn that into a front. So in this example, yeah, that's going to be the cold front. And once again, if we do a cross section, we should find the frontal surface right in there. And there it is. Well, I think that's a good stopping point. If you enjoy these lessons, definitely comment or write me at tim.vasquez@weathergraphics.com and let me know if you're enjoying these videos. If it's a little bit too dry and not really appropriate, if you're trying to relax in the evening and just kind of see what's going on, that's fine. Let me know. I want these videos to be the thing that most of y'all want. So definitely give me that feedback. Okay, take care. We'll see you all tomorrow. Bye-bye.